Welcome to Math with EJD. In this video, I'll be talking about the QR computation of eigenvalues and eigenvectors. This is a numerical. It is a very good example of numerical computation method for eigenvalues and eigenvectors. Previously, we had dealt with power method. I have two videos on that. Trying to buttress that fact. And I've done and I've also shown another method, which is an inverse iterative method. So in this video, our focus is going to be on the QR method. Then later, I'll be talking about the Rayleigh quotient method. So talking about the QR method, right? It's an iterative algorithm. The QR method is an iterative algorithm used to complete the eigenvalues, used to compute the eigenvalues and eigenvectors of a square matrix. It uses the QR decomposition, where a matrix A is factored into product of an orthogonal matrix Q. Okay, so we factor the matrix a given matrix A, into the product of an orthogonal matrix Q and an upper triangular matrix R, such that A becomes QR. Now, if you want to know about special matrices, my very first playlist on this channel was about matrices. So if you want to check that up, I think one of the videos that talks about special matrices like idempotent matrices and things like that, and orthogonal matrix and all of this. So this method actually proceeds by iterating with A1. So once you decompose matrix A into Q times R, Q being an orthogonal matrix and R being an upper triangular matrix, so the method then proceeds by iterating with A1 equals RQ. So the QR you got, you reverse it and multiply, and that gives you a matrix A1. So then so with that, you update A at each step, and the process converges to a matrix whose diagonal elements are the eigenvalues of A. So that means by the time you keep doing this, you're going to finally get to a point where you have a matrix like this. So you're going to have an upper triangular matrix, and here you're going to have yeah, this is be like lambda one, and this will be lambda two. Then you can have whatever in these places. There may be zero or whatever. So, but then what you have at the principal diagonal will be the matrix, it will be the eigenvalues you are looking for. Okay. So, and one process that is necessary for orthogonalization to make a matrix orthogonal is the Gram-Schmidt process. So the Gram-Schmidt process is an orthogonalization method that transforms a set of linearly independent vectors into an orthonormal set. So this process is used to obtain the orthogonal matrix Q in the QR decomposition. And these are the steps involved. I mean, just to buttress the point. So the first step is you start with a matrix A. So you have your given matrix A, whose eigenvalues and eigenvectors you're interested in getting. Of course, usually you use this, you probably have to use this method if the regular methods won't work, or they won't give you a very nice answer. Of course, we end up using such matrices just to drive home the point, just to make it easy to comprehend the steps. So for QR decomposition now, that's the second step. So at that level, you perform the Gram-Schmidt process to decompose A into A equals QR, where Q is an orthogonal matrix and R is an upper triangular matrix. I think orthogonality is the fact that if a matrix is orthogonal, for instance, if Q is an orthogonal matrix, then Q transpose Q, that is Q transpose multiplied by Q, would give you identity matrix or so. I think that's what the idea of orthogonal matrix is. Then three, you update the matrix, and to update the matrix, you form a new matrix A1, which will now be RQ. You'd have decomposed A into QR. Then if you reverse it, you get RQ. So when you multiply out RQ, you're going to get a new matrix A1, which will form your new A, and then you repeat the first step. Now you repeat the QR decomposition on the updated matrix A1. And then for convergence, so as the iterations progress, right, the matrix A1 will converge to an upper triangular matrix, and its diagonal elements, just like what I showed at the other time, the diagonal elements will approximate the eigenvalues of A. Then at the sixth step, you have the eigenvalue approximation. So just like we said already, the diagonal elements of A1 after many iterations will approximate the eigenvalues of A. Now, because many iterations may be involved and the process can be really tedious, maybe after doing one Gram-Schmidt process, I'll just not bother again. I'll just show you the Python code to make it happen. Then The seventh step will be the eigenvector computation. So the eigenvectors can be extracted from the columns of the matrix Q. All right. So you extract the eigenvalues from the column of matrix Q. So let's take the example we've been taking all along. So given A equals 4, 1, 2, 3. So step one, in step one, we are going for the QR decomposition, which is like the crux of this method, the QR decomposition, which makes A into the product of orthogonal matrix Q and upper triangular matrix R. So step one, QR decomposition, of course, using the Gram-Schmidt process. So under that step, right, the first thing we need to do, we start with matrix A. Okay, so A is equal to 4, 1, 2, 3. That's the matrix we start with. A is 4, 1, 2, 3. That's the first thing. Then we apply the Gram-Schmidt process to the columns of A. And to do that, we have, of course, from A, right? This is the first column is 4, 2. The second column is 1, 3. Okay? So those are the columns. So it means that A1 is equal to 4, 2. And A2 is 1, 3. A2 is 1, 3. Like that. Then we go for the next step. So still on this, like, this is the Gram-Schmidt process. So under this process now, we have step A, which is to normalize A1 to find Q1. So the norm of A1 now is equal to, that will be the norm of 4, 2, the matrix. That means we have square root of 4 squared plus 2 squared. That's the meaning of norm. That's square root of 16 plus 4. That is square root of 20, which is square root of 4 times 7. That's 2 root 5. So it means that norm of A1 is equal to 2 root 5. Settled. Then, having done that, we now go for Q1. Q1 is A1 divided by the norm of A1. And we know A1 is what we just have, 4, 2. So 4, 2 there, divided by the norm of A1, which is 2 root 5. So in essence, we have 1 over 2 root 5 into 4, 2. Okay. So that's like, so it means we have 4 times 2 root 5. So 2 cancels 4. So that gives us 2 over root 5. Then 2 cancels to here. You have 1 over root 5. So that is our Q1. So don't forget, Q1 is 2 over root 5, 1 over root 5. Also settled. Then we go for the step B under the second step. Under the step 2, under the big step 1 rather. So B now, so we have to compute the projection of A2 onto Q1. But compute the projection of A2 onto Q1 to find the, so we want to find the component of A2. A2 is 1, 3 from what we have, right? So from A2, orthogonal to Q1. Okay. And to do that, we first calculate the inner product. That's A2 Q1, the inner product. So you remember A2 will be 1, 3. now we have to transpose it because we know Q1 is 2 over root 5, 1 over root 5. That's the Q1 we got. And from that simply means we have, 1 time, so that's 1 times 2 over root 5, 3 times 1 over root 5. So that is, so 1 times 2 root 5, that's 2 over root 5, plus 3 times 1 over root 5, that's 3 over root 5. So that means that we have root 5 as LCM. So that's just 2 plus 3 in short, and that is equal to 5 over root 5. So if you rationalize, you have 5 over root 5 times root 5 over root 5. That's how to rationalize this kind of thing. So that is 5 root 5. 5 times root 5 times root 5 is simply 5. So this cancels out. So we see that inner product is A2 comma Q1, and that is simply equal to root 5. So that is taken. So after doing that, now we compute the projection, of A2 onto Q1. Now it's A2 onto Q1. In that case now, we have the projection. We have the projection of A2 onto Q1. And that simply means we have the inner product, A2 comma Q1. I'm trying to be sure the A2 and Q1 are not the same. So A2 and Q1 divided by the square of the norm of Q1, okay? All of that multiplied by Q1 itself. So, of course, A2 Q1, we already know that to be root 5. So this would be root 5 up there. Then the norm of Q1 all squared. So Q1, Q1 is 2 root 5, 2 over root 5, 1 over root 5. So that's like the norm of 2 over root 5, 1 over root 5, all squared. So this now multiplied by Q1 again, that's 2 over root 5, 1 over root 5. Okay. So that continues, and we have root 5. And for the norm, right, we know that should be norm itself is square root of 2 over 5, 2 over root 5, all squared, plus 1 over root 5, all squared. Then everything is now squared, multiplied by 2 over root 5, 1 over root 5, like this. So still on it, we have root 5 up there, all over 2 cancels roots. So when we square 2 over root 5, that's 4 over 5 plus 1 over 5. So that's what that gives. This all multiplied by 2 over root 5, 1 over root 5. So that is equal to root 5 all over, the LCM of everything under there is 5. So that's 4 plus 1 multiplied by 2 over root 5, 1 over root 5. So that is equal to root 5 all over 1 into 2 over root 5, 1 over root 5. So the projection, we are still talking about the projection of A2 onto Q1. So we can finalize now and say the projection of A2 onto Q1 now is equal to, so if you look at this now, this is basically 2, 1 in short, because root 5 cancels out in each case. So that projection is 2, 1. So we have that. So still talking about this, we now have under the step 2, under the sub step 2, now we have the next one, which we can call C. So now we want to subtract the projection from A2 to find R2. And R2 is the component. It is the component. R2 is a component of A2 that is orthogonal. That is orthogonal to Q1. Okay. So now we have R2 equals A2 minus the projection the projection of A2 onto Q1. Okay, so that is simply, A2 is 1, 3. Projection of A2 onto Q1 is just what we just got as 2, 1, and that's simply minus 1, 2. So in short, R2 is minus 1, 2. Okay, then step 4, step 4, right? D. So now we need to normalize R2 to find Q2. Normalize R2 to find Q2. So the norm of R2 now is equal to the norm of R2 is minus 1, 2. Okay. So we have that to be square root of minus 1 squared plus 2 squared. And that is square root of 1 plus 4. That is root 5 in short. So we can now have Q2 to be equal to R2 over the norm of R2. So R2 itself is minus 1, 2. The norm of R2 is root 5. So in short, we have minus 1 over root 5 all over 2 over root 5. Or if I want to make it a bit clearer, so I can say 1 over root 5 into minus 1, 2, and that is minus 1 over root 5, 2 over root 5, 2 over root 5. Okay, so that's Q2. Now we have the orthogonal vectors. The orthogonal vectors are actually Q1 and Q2 that we have found. So we can go to this is everything we've been doing is sub step 2 under step 1. So we go back to sub step 3 under step 1. Okay, so that is 3 now. So here we now want to construct the matrix Q. Construct the matrix Q. And we already have an idea what that should be, right? So the matrix Q consists of the orthogonal vectors Q1 and Q2 as columns. Okay. In essence, we are saying that Q is Q1, Q2, meaning that Q is actually Q1 is 2 over root 5, 1 over root 5, whereas Q2 is minus 1 over root 5, 2 over root 5. That is what our Q is. Okay. So the fourth sub-step would now be to construct the matrix R. Construct the matrix R. So we have got our orthogonal matrix. This is our orthogonal matrix Q. This is orthogonal matrix Q. It's QR decomposition, orthogonal matrix Q. This is it. So we now want to construct the matrix R. So the matrix R is an upper triangular matrix. It's an upper triangular matrix. And it can be computed. As the dot products, of the original columns of the dot product of the original columns of A with the orthogonal vectors, with the orthogonal vectors Q1 and Q2. So we have R to be Q1 transpose A1, then Q1 transpose A2, then 0, and then Q2 transpose A2. So let's go for that. So R, what is Q1 again? Q1 is 2 root 5, 1 over root 5. That is the transpose of that. So we have Q1, 2 over root 5, 1 over root 5. That's Q1. That's Q1 multiplied by A1. A1 again, don't forget A1 from the beginning is A1 is 4, 2. A2 is 1, 3. Okay? A1 is 4, 2. A1 is 4, 2. Q2 is 1, 3. So A1 is 4, 2 like this. Then Q1 transpose again, that's 2 over root 5, 1 over root 5. You know, we have transposed it, that's why it's like this. A2 is 1, 3, as you remember. So this is 0 here, easy. Then Q2 transpose, what is Q2? Q2 is minus 1 over root 5, 2 root 5. So that is minus 1 over root 5, 2 over root 5, multiplied by A2. A2 again is 1, 3. So this is the kind of thing we have. So, I mean, this is just easy because 2 root 5 multiplies 4, 1 root 5 multiplies 2. Just like 2 root 5 multiplies 1, 1 root 5 multiplies 3, 1 root 5 multiplies 1, and then 2 root 5 multiplies 3. So let's go for all that. So now we have 4 times 2 over root 5 multiplied by 4, that's 8 over root 5, okay, plus 2 over root 5 up there. Then coming here, we have 2 over root 5 plus 3 over root 5. That's for this now. Then, of course, this is just 0. And here, this is minus 1 over root 5 times 1. That's minus 1 over root 5 plus 2, 2 times 3, 6. That's 6 over root 5. Okay? That's 2 over root 5 multiplied by 3. So we can tidy this up. So R now is equal to, this is 10 over root 5. This is 5 over root 5. This is 0 here, and this is also 5 over root 5. So that R now is equal to 10 over root 5. We can normalize just like we did before. That's 10 root 5 over 5. That's multiplied by root 5, root 5 over root 5. Then here, this is 5 over root 5, all over root 5. This is 0, and this is also 5 root 5, all over, oh, 5 root 5 over 5, sure. Because root 5 times root 5 is going to give us 5 each. Okay. So our R is 5 here is 1. This is just 2 root 5. This is root 5. This is 0. This is root 5. This is root 5. So that is simply what our R looks like. That is our R. So now we have got what's happening here? Why is that 0? What is Q1 transpose? Q1 transpose is minus 1 over root 5, 2 root 5. Then A2 is 1, 3. So this is minus 1 over root 5. Yeah, we are good. Yeah, that's fine. That's fine. Okay. So we can then conclude that thus the QR decomposition, the QR decomposition of A is A equals QR, which is equal to 2 over root 5 minus 1 over root 5, then 1 over root 5, 2 over root 5, and all of that multiplied by, so you can see this is, so that's the orthogonal matrix Q, and then you now have the upper triangular matrix. This is 2 root 5, root 5, 0, root 5. So we have done the QR decomposition safely, and that takes us to step 2. So step 2, everything we've done so far is just step 1. Step 2, now we now update the matrix. A1 equals RQ. Okay. So we update A1 equals RQ. So that means we have A1 equals RQ now. And that is equal to 2 root 5, root 5, 0, root 5. Then we have Q. Q is 2 over root 5 minus 1 over root 5. Then down here, 1 over root 5, then 2 over root 5. Okay, so we can get our A1. I guess I'll just do dash. Okay, should I just do it? Okay, let me just let me be patient. This is 2 over root 5. This is quite a process, right? 2 over root 5. I write it twice. 2 over root 5, 1 over root 5. Then we also, so we now put this one over it. So this is 2 over root 5. Then this is root 5. Then here we have 0, and this is root 5. Okay. Then same, we write minus 1 over root 5, 2 over root 5. We write that twice again. So minus 1 over root 5, 2 over root 5, 2 over root 5. Then we put all this over it again. This is 2 over root 5. This is root 5. And then this is 0 again, root 5. Okay. So that is going to be our A1. That is going to be our A1. So we have this. So what is A1 now? If I can just get the answer straight, I'll be good. So that this will be 4 over 5 up there, and this will just be 1. Okay, so we have 5. Then here we have, this will be minus 2 over 5, right? That is minus 2 over 5, I believe, because minus 1 times 2 is 2, root 5, root 5. Okay, we should be adding these things together, sorry. Okay. So this is 2 times 2, 4. Root 5 cancels. So that is 2 over 5 plus, here, root 5 just cancels that. So that's 2 over 5 plus 1. That's 2 over 5 plus 5 over 5. I think that should be 7 over. Or let me not jump. Let me just do it the way it is. I was thinking I could just jump. So this is that up there. We have 4 over 5 plus 1 over root 5 times root 5. Root 5 just cancels out. So we have 1 over 5 plus 1. Then the other side we have minus 2 over 5 is minus 2 over 5 plus root 5 cancels out. So we have just 2. Then down here we have 0 plus 1 again, because 1 over root 5 times root 5 is root 5 cancels out. Then at the other side, minus 1 over root 5 times 0, that is just 0 plus 2. Okay, so that A1 now is equal to 4 over 5 plus 1. That's 4 over 5 plus 5 over 5. That is 9 over 5 here. Then here we have minus 2 over 5 plus 10 over 5. That is 8 over 5. Okay, because 2 is like 10 over 5. So we can just say 10 minus 2, 8. Then this is 8 over 5. Then here, this is 1 and this is 2. Okay, so that's what our A1 looks like. That's what A1 looks like. So we are supposed to do that long journey we did with A. We now do it with this one again. You can see it's not a small thing, right? We can turn all this to decimal if you like, but because we still have a long way to go, right? So what I'm going to do is, okay, now that takes us to step 3, right? So I'll just mention step 3, but I won't do the step 3 because it's going to be really, really tedious, as we know already. So I go for step 3. Step 3. So what you did with A before, so you now have, this is now going to be A1 again, and this will be A2, columns like that. And then you go and do the process again. So I'll just write it, iterate. So do the same again. Break A1 into RQ again. So you can call it R1, R1, Q1 if you like. So step 3, iterate and iterate until convergence. Let me put it that way. Iterate until convergence. Okay, iterate until convergence. So in essence, we repeat the QR decomposition. Repeat the QR decomposition on A1 to refine. So far, normally the eigenvalue should be something close to this. I mean, this 2 is already correct because it's going to be 2 at the end of the day here. But this 9/5 is still far from the call. So that's why we have to keep iterating until we get there. So we repeat the QR decomposition of A1 to refine the eigenvalue estimates. Eigenvalue estimates. Okay. After multiple iterations, the matrix A1 will converge. In fact, maybe I should have just called that matrix AN or something. So the matrix A1 will converge. The matrix A1 will converge to an upper triangular matrix, The A1 we got there is still not an upper triangular matrix because we still have everything in order. So we'll convert to an upper triangular matrix, okay, whose diagonal elements, are the eigenvalues, are the eigenvalues of A. Okay. So after several iterations, the matrix will converge to something like this. A1, which is approximately lambda 1, 0, 0, lambda 1. So just like I told you, that 2 is already giving me hope because one of the eigenvalues of this matrix is 2, but the other one is 5. So this other one is still far from it. So we now see that the diagonal elements, lambda 1 and lambda 2 are the eigenvalues of A. They are the eigenvalues of A. So that takes us to step 4. So step 4 now. In step 4, we are talking about eigenvalue. What we really need, eigenvalue and eigenvector approximation. Okay. So that's the 4th step. So the eigenvalues of matrix A can be approximated from the diagonal elements on the converged matrix. Maybe after A1, you can go to A2 until you get to a particular place where the value actually converges. So actually, for this example, after convergence, the eigenvalues are approximately okay, lambda 1 is roughly 5 and lambda 2 is roughly 2, like I said the other time. So eigenvectors, the eigenvectors corresponding, the eigenvectors corresponding, the eigenvectors corresponding to this eigenvalues can be extracted, from the columns of the matrix, from the columns of the matrix Q at each iteration, at each iteration. So these eigenvectors will be the direction vectors, will be the direction vectors, the direction vectors along which the transformation matrix, along which the transformation matrix A acts by stretching or compressing. Okay. Now, having said all this story, since it's going to be a tedious process if we want to do it manually all the way, now let's finish up the process by looking at what the Python code for QR decomposition. So you can see this right here. So line 1, we import numpy as NP because we need to do the numerical some numerical computation, right? So we have the Gram-Schmidt process defined from line 4 to 7. So we have Gram-Schmidt, we have M and N, the matrix A, the Q, which is the orthogonal matrix, R, which is the upper triangular. We define all of that. So we now say for I in range N. So start with the column vector AI, the 4-2-1-3, that kind of thing. So that's all of what is happening in all of this place. Then the normalization is happening here also. That is coming from linear algebra, which we find in NumPy. Then we now have the QR method for eigenvalues. So the QR method is also defined from line 25 here. So QR method is defined from line 25, and we get all that. Then Gram-Schmidt, so we now have the iteration starting here. So Gram-Schmidt is summoned since it has been defined at the top. So at the end of the day, if we run this, you can study the code for better understanding. You can also find it in the description on Facebook. For YouTube, it's not I'm not able to do it because of some special characters. The corner stuff, the corner brackets are not allowed on YouTube description. So you can see there to get to converge, right? We have 5 iterations till convergence. So so you can see at the end of the day, the eigenvalues are 5.00 and 1.99, which is roughly 2, right? So look at the first iteration. If you remember what we got there, when we got our first RQ, so it's so the matrix, we have 5, 2, and all this. That's iteration 1. The orthogonal basis, when you break it down, you have 0.89, 0.8. Then here, 4.4 something. I think that we had, is it 8/5 we had there also? So based on our own method, so we have this. So and this keeps going on till we finally get the 2 eigenvalues, 5 and 1.9. So try to understand the code properly, and that's how it goes. It's really a tedious process. This has been such a long one. So you need some patience to really understand it. So in conclusion, right, we see that the QR method is such a, I think that it's the longest so far. So the QR method using the Gram-Schmidt process is an effective technique for finding the eigenvalues and eigenvectors of a matrix. The method converges iteratively on the diagonal elements of the matrix. A1 obtained after multiple iterations will approximate the eigenvalues of the original matrix A. The eigenvectors can be computed from the orthogonal matrix Q at each step of the iteration. So the orthogonal, the eigenvectors will just be your Q1 and Q2 that we got the other time. And that's how it goes. So if you have subscribed to this channel, thank you for subscribing. If you have not, please go ahead and do that because there's a lot more to learn. And don't forget to hit the subscription button so you can always get alerted each time any video is released. Comment, let me know how helpful these videos are. Let me also know if there's a topic you like me to teach or a problem you like me to solve. Then like and share so that more people can have access to this great learning. Till I come your way again, keep doing math right. Bye.